Hello everyone, welcome back to Nated Engineering. Today we are doing an exercise on gradually applied loads. The exercise that we are doing reads as follows. A member consists of two different square bars. One section is 50 mm square with a length of 600 mm and the rest of the bar is 80 mm square with a length of 1 meter. The member is subjected to a tension of 100 kilonewtons and Young's modulus is 206 gigapascal. And then the questions. Question number 1, they say calculate the strain energy in the member. Question number 2, they say calculate the total change in length. Question number 3, calculate the total strain in the member. Question number 4, they say calculate the maximum stress in the member. So we are going to start. Every time you are doing an exercise on whatever subject that you are studying, my advice to you is always create a diagram. Especially with strength of materials and structures. You cannot solve a question on strength of materials and structures without a diagram. The diagram is part of the solution, so you must draw it. We're going to start with our question 2.1. We say calculate the strain energy in the member. Strain energy is given by U, it's equals to half times F x T, which is the total change in length. We are dealing with 1, 2 objects. Therefore, before we come to this formula, we need to fix this problem. Our change in length, total change in length will be equal to change in length number 1 plus change in length number 2. The information that we are given will allow us to use such a formula. F L divided by AE. And this will be length number 1 and this will be area number 1 plus F length number 2 divided by area number 2 times the Young's modulus of elasticity. We are going to take the force and the Young's modulus of elasticity as common since they are the same throughout. And then we are going to say force divided by the Young's modulus of elasticity, in bracket it will be the length, which is length number 1, divided by the area, which is area number 1, plus area number 2 divided by length number 2 divided by area number 2 rather. And then from here we are going to substitute. What is our force? Our force is 100 times 10 to the power 3, which is kilonewtons. What is our Young's modulus? 0 is 206 times 10 to the power 9, that's a giga, times our length number 1, it's equals to what? It's equals to 0.6 divided by the area, which would be 0.05 times 0.05 plus we come to this part. What is our length? Our length is 1 divided by what? The area, which is 0.08 times 0.08, and then we close the bracket. Working that on the calculator, our total change in length is equals to 1.924 times 10 to the power negative 4. This is the change in length, and this it's in meters. And then from there, it's then that we can now use the formula to calculate for the strain energy, the total strain energy, which will be half times the force, which is 100, times 10 to the power negative 3, it's just 3, times the change in length, the total change in length, which is 1.924 times 10 to the power negative 4. And that will give us a total strain of 9.62 joules. And then we go to question number 2. Question number 2, they say, calculate the total change in length. We already did that. This is the total change in length. This would be 2.2. And then we go to the next question, which is 2.3. 2.3, they say, calculate the total strain in the member. Let's erase this, all of it. Like that. Then it's 2.3. We are looking for the total strain in the member. We have two sections. Therefore, we know that total strain is given by strain number 1 plus strain number 2. The formula to calculate strain is change in length per unit length. Therefore, we are going to say change in length number 1 divided by length number 1 plus change in length number 2 divided by length number 2. We are going to substitute our change in length. We know change in length is given by FL divided by AE, which will be equals to FL divided by AE, all divided by length number 1. This is also length number 1, plus FL2 divided by A, this is also A1, this will be A2, E divided by length number 2. This and this, this and this will cancel out. Then we will be left with a formula that is like this: F divided by area 1 modulus of elasticity, F divided by area 2 modulus of elasticity. And then from here, we are going to take the force and the modulus of elasticity because they are the same. We are going to take them common. Let's erase this. We are going to say force divided by the modulus of elasticity times, in bracket, 1 over area number 1 plus 1 over area number 2. And then from here, we can do our substitution. Our force is equals to 100 times 10 to the power 3. Our modulus of elasticity is equals to 206 times 10 to the power 9, in bracket. Area number 1 will be 0.05 times 0.05 plus area number 2 will be 0.08 times 0.08 close bracket. And then from here, we are going to get our answer as 2.7 times 10 to the power negative 4, which will be our total strain. That is 2.3, and then we go to 2.4. 2.4, they say, calculate the maximum stress in the member. We know the maximum stress will occur in the section with the smaller cross-sectional area, which will be the 50 by 50, a section which is 50 millimeters by 50 millimeters. Therefore, 2.4, we are going to say the maximum stress, which is given by force divided by area. That would be area number 1. It's 100 times 10 to the power 3 divided by 0.05 times 0.05, which will give us our maximum stress is 40 megapascal. If you are not sure which one will give you the maximum stress, calculate for stress number 1 and stress number 2, and then compare the two. But at the end, you must indicate which one is the maximum stress. In this case, the maximum stress is 40 megapascal. And that is the end of our question. I will see you on the next video.